Issac Kim is an assistant professor at computer science at UC Davis. He is a theorist working on quantum information, quantum computing, and quantum manifold physics. While Paul is quantum application architect at PsiQuantum with main interest in developing quantum software with focus on applications and compiling. And we'll hear some great presentation about fault-tolerant resource estimation. So, yeah, please start.
Alrighty. Yeah, so thanks for the introduction. Also, thank you for inviting us to speak here. So my name is Walt Pohl, and Isaac and I will be talking about this paper that we put on the archive sometime last year, fault-tolerant resource estimate for quantum chemical simulations. And this is work that we did with our colleagues at PsiQuantum and also a collaborator, Issac Kim at Daimler, at the time at Daimler. So the scope of the paper is really twofold. First off, we did a tip-to-stern resource estimate for simulating battery chemistries on a fault-tolerant quantum computer. And this involves starting from a particular use case for estimating energies, going to hardware agnostic metrics like number of logical qubits and, in our case, T-gates, and then boiling that down to some particular runtime and footprint estimates for the size and the length of the computation in terms of like minutes and hours, and that kind of thing. Second part of the scope is about the serial versus parallel application of gates. So we studied the degree to what degree the application of these gates can be parallelized in order to speed up the overall computation. So a lot of the paper focuses on how to structure the algorithm so that we can realize gate depths that are substantially smaller than gate counts. And then we detail an architecture and compilation method to execute multiple gates in the same clock cycle. So I'll quote the result of the physical resource estimate, but in the interest of time, really we'll focus on the parallelization aspect, both at the algorithmic level and at the compilation level. So I'll talk a little bit about the algorithm, give kind of maybe not so many details, but some intuition of what's going on. And then Isaac will detail the compilation method to execute multiple non-Clifford gates in the same clock cycle. Alrighty, so we start with some use case. In the paper, we looked at 7 different molecules that are often used in battery chemistries. So these are various combinations of some electrolyte solvents and salts with lithium and some variants. And for each of these 7 molecules, we determined the estimates under 5 different basis sets, ranging from some minimal basis sets that are easier to simulate, but maybe not so chemically accurate, up to some larger basis sets that are chemically accurate for these molecules and harder to simulate. And just to quote some results, when I do, I'll be talking about the smallest instance we considered and the largest instance we considered. So the algorithm we're looking at, we're in the world of fault tolerance, so it's a different regime than Jerome's talk. The kind of algorithm we look at is quantum phase estimation, where the goal here is to estimate the energy E in the static Schrodinger equation up to some error epsilon. And in particular, we make use of block encoding techniques. So these are like modern alternatives to product formula techniques like Trotter. The idea here is instead of trying to approximate e to the minus IHT, we instead try to embed this non-unitary operator, the Hamiltonian. We try to embed it into some larger unitary matrix. So we increase the Hilbert space so that in some subspace where a bunch of ancilla are in the 0 space, we can say that the Hamiltonian lives there. And this is what we mean by block encoding. And importantly, these kinds of algorithms scale with 2 quantities related to the size of the Hamiltonian. One is the amount of information gamma, which you can think of as like the number of terms that you're trying to load from your Hamiltonian. And the other is the norm of the Hamiltonian, which is kind of like a rescaling factor so that we have the promise that this block encoding matrix is indeed unitary. We have to rescale our Hamiltonian. And so to do phase estimation on these kinds of block encodings, they scale like the following. So we have the actual cost of doing this block encoding circuit scales like the number of terms, or square root the number of terms. And then to do phase estimation up to some error epsilon, we need to query this unitary some number of times. And the number of times scales proportionally to the norm and inversely proportional to the epsilon that we're trying to estimate up to. So this is kind of scaling to have in mind in general for block encoding type algorithms. But we actually consider the use of Hamiltonian factorization. So in second quantization, a lot of the most competitive resource estimates have been making use of so-called factorizations. And the idea here is that starting from this, like the canonical second quantized fermionic Hamiltonian, we have some 1 electron terms, we have some 2 electron terms. As Jerome mentioned, the 2 electron terms, this scales like n to the 4th, where n is the number of orbitals in whatever basis set you've chosen. And the idea of a factorization is to try and make the amount of information that you're loading smaller, and also to try and make the norm itself smaller. So the idea here is that you can re-express this Hamiltonian and then perform some kind of a truncation, such that instead of scaling as n to the 4th in the naive case, you can instead scale closer to n cubed for single factorization and double factorization, two techniques. And the most competitive technique called tensor hypercontraction scales sort of like n squared. And likewise, the norm itself for these techniques like tensor hypercontraction, double factorization are much smaller, which is good because we scale with both of these quantities. And so we want to, make them as small as possible. In our paper, we consider double factorization, but I'm not going to get so into the details of any particular factorization. I kind of want to give some intuition for how one block encodes a factorized Hamiltonian in general. So we can start again with this, the canonical form, and this HPQRS tensor here in the Coulombic term. This is an n by n by n by n tensor. And what you could do is you could express it as a sum of tensors of a different, smaller rank. And so there's many potential ways that you could do this. Like I said, double factorization or tensor hypercontraction. But a common feature is that you'll end up with something like the following. You have H tilde, which I'm basically ignoring the 1 electron term. You have H tilde, which you can express as a sum over M, which is not n. And now we have this different tensor, HPQRS, but with a tilde. And depending on the kind of factorization you choose, this could have many, many different shapes. So I'm going to try and remain agnostic about it. But the idea here is that you could truncate M so that this sum ends up scaling instead of like n to the 4th, you could scale like n cubed or n squared, depending on the particular choice. So this sounds really nice. But there's a potential disadvantage, which is that we know how to block encode the vanilla Hamiltonian very well. So if you apply Jordan-Wigner to this, this will just look like a weighted sum of Pauli's. And Pauli's, we know how to implement those on quantum computers. We're very comfortable with this. But you'll notice that this H tilde is not really a weighted sum of Pauli's. In a lot of these factorizations, what you end up with is a weighted sum of what we can call basis rotated Pauli's. Basis rotated because we have this number operator here in the middle, which under Jordan-Wigner is just a simple Pauli Z. Like this is a very easy thing. But before we can apply the easy operator, we have to do some kind of basis transformation. So you'll see that the number operator is sandwiched between these this U and U dagger. And the idea is that when we do a factorization, we now live in this new basis. And so we need to rotate out of that basis to apply our easy Pauli and then rotate back into that basis. So you can see this pictorially as in the following way as a circuit. And if we color code this, what we have here is we have some coefficients that we prepare in green. So we prepare on some register of qubits, a superposition state over various coefficients. In blue, we have this basis transformation that I'll talk about in a second. And then in red, we have our simple Pauli that's easy to do. Really, the brunt of the complexity of these kinds of algorithms comes from this blue step. It's performing this basis transformation. And there's two unitaries that are really important here. One is a data loader unitary. This is where you give me some index and I give you a term loaded from some list queried by that index. And here, this data loader is loading the various angles that you need to perform rotations by. And so this is a pretty, big chunk of circuit. This decomposed into many, many gates. And then once you have loaded these angles, you need to control on them to apply your basis transformation rotations, which turn out to be Givens rotations. So this blue chunk of circuit is really where the complexity comes from. Like I said, I'm just trying to give some intuition. So I'm just going to go straight to quoting some results now, so we can get on to the next part. But in the world of fault tolerance, what we care about are logical qubits and also T-gates. So T-gates are these non-Clifford gates that require a dedicated portion of your quantum computer to be preparing some magic state. And so we count those up and we can consider Clifford gates effectively free. And also it turns out to be useful to talk about computational volume. So this is just a product of qubits and T-gates. And this is because it's easy to trade off between the two. And so it makes sense to try and minimize one quantity, like their joint quantity. So just to quote some numbers, in the small instance, which maybe doesn't sound so small, but in the small instance, we have something like close to 3,000 qubits with a T count 10 to the 10. The big instance, we have something like 10 to the 5 qubits and a T count of 10 to the 14. These values, not so important. These comes from the factorization. And then, like I said, I'm just going to quote the physical level costs. There's not so much time to get into it, but these physical level costs try to account for the overhead due to fault tolerance and error correction. So in particular, we consider surface code style error correction. We perform our gates via lattice surgery. We can talk about this later if you have questions on it. But what we care about at the end of the day is footprint and runtime. And so you could think of footprint as kind of like physical qubits. And if we do this, we see that we have something like a few million physical qubits in the small instance with a runtime on the order of minutes. So this is close to half an hour. And then in the big instance, we have a footprint close to like hundreds of millions of qubits, physical qubits, with a runtime of I think about 2 weeks or so. Okay, so why do we say T-gates are so expensive to begin with? This is because usually you could see these rectangles as like representing, if you want, a 2D array of physical qubits. Our device has some portion of it reserved for actually storing the computation. So this is where your wave function lives in your algorithm. But there's actually a huge chunk of your footprint dedicated to churning out magic states. So magic states are kind of like the fuel that you need to actually implement a T-gate. So every time that you see a T-gate in a circuit, it actually required this giant chunk of your footprint to make the T-gate. And the reason that the estimates are so big initially is because we assume, and the literature tends to assume, a serial application of gates. Since this factory is so large, it really only makes sense in general to think about having a single factory making one T-gate at a time. But what we found actually is that in this regime where we have so many logical qubits, it turns out that the T-gate factory is actually remarkably small in comparison to the rest of the computer. I'm going to skip over this, but this kind of motivated the idea of trying to parallelize the algorithm. So in particular, earlier I claimed the volume that we use is like qubits times gate count, but this is actually an upper bound on what the overall volume could be. In principle, if your depth was much smaller than count, you could try and exploit this, and this would be like a lower bound on which volume you could use. And so I think the intuition here is that if your factories are cheap, the relative cost of adding more of them is very, very low. And so you might want to add more magic state factories in order to churn out multiple T gates at the same time. I'm going to skip over this, but suffice to say, the difference between the depth and the count for these algorithms is very large. It's usually about an order of magnitude for all instances that we considered. And so this kind of motivates the following, which is that, just to summarize, when you have many, many qubits, magic state distillation is pretty cheap. If magic state distillation is cheap, you can make multiple magic states in parallel. And if you can use multiple magic state factories, you need your algorithm to be parallelizable, which we just showed is the case. The depth is very small compared to the count. And you need the consumption of these gates to be very, very fast. So here I'll hand over to Isaac, who will detail the compilation.
Right. So whilst we're switching slides, there was a question. So I think the question is like, how is the data loader in the circuits determined? And it should be clarified that we actually consider the double factorized version of the Hamiltonian, not the tensor hypercontraction. And I believe this rotation that corresponds to the tensor hypercontraction case. So I cannot answer that aside from just forwarding to the paper. But in the double factorized case, it's relatively more straightforward because you're expressing the Hamiltonian as a sum of like square terms. So like a normal qubitization trick, like with some modifications, still works. But we can talk more about that after I finish this part. Okay, so I'm going to talk about the compilation part. So there's a question about, given these algorithms, like how can we actually implement these algorithms on a like fault-tolerant quantum computer? And one thing that I want to emphasize is that the gate model for the fault-tolerant quantum computer is somewhat different from the let's say NISQ quantum computers. So as Will already alluded to, the dominant, the most expensive part of the computation is the T gate. And the basic paradigm is that you have a Clifford gate and the T gates. And over the past few years, people realized that a more efficient way to understand these fault-tolerant quantum compilation is to basically decompose everything in terms of these, what we call as Pauli product rotations and Pauli product measurements. So Pauli product rotation is an exponential of some angle times some arbitrary Pauli. The important point here is that Pauli, this is not just like a single or 2 qubit Pauli, but an arbitrary like an n qubit Pauli. So you might think that this is a highly non-local operator, so and as such very difficult to implement, but actually that's not quite true. So insofar as you do error correction, the cost of implementing these non-local operators is actually just adds a very negligible cost on top of error correction. And in fact, if you consider a completely general Pauli product rotation, which of this form, this can be decomposed into several steps, all of which involve a single magic state here and Pauli product measurements. So this is the basic paradigm in which we think about compilation. So because every quantum algorithm can be decomposed into a sequence of Pauli product rotations, which can be subsequently decomposed into a sequence of Pauli product measurement, it's very important to understand what is the actual cost of implementing a Pauli product measurement. So naively speaking, people already knew that if you have like n qubits, and if you have a, let's say a surface code based architecture with a code distance of d, the time to do this scales linearly with the code distance. The space scales quadratically with distance. And one thing that we wanted to emphasize in this work is that there's a scenario under which you can reduce the time cost. So the space cost remains the same, but you can reduce the time cost up to some caveats, which I'll explain in more detail. So the reason why we have a let's say the time cost that scales linearly with D is because if we decompose this Pauli product measurement into a sequence of elementary single and 2-qubit gates, those elementary gates in its most naive form takes a time that is linear in D. So you already know what the Pauli operators are. So for implementing those operators in the surface code-based architecture, it suffices to do it in constant time, because this is simply just a tensor product of Pauli's, and that can be done in like a single time step. But if you want to apply Clifford gates like Hadamard, phase gate, or CNOT gates, the leading strategy to do this is to implement what is known as lattice surgery, and this takes a time that scales linearly in D. But there are actually alternative ways to implement these gates. This was discovered by these folks and also by Musa. And the long story short, you can actually implement a complete set of Clifford gates in constant time using a technique called as transversal gates. So there are actually a bit more detail than this, because if you just use these transversal gates in these previous papers, you will the resilience of your code against errors will diminish a little bit, and we have, I think, good ideas to combat that issue, but perhaps that's too much of a side comment. I'll be happy to talk about it if anybody's interested. But at the high level, once you accept that there are these constant time gates that you can implement, which can be implemented using a folded version of the surface code, you can imagine like folding up your system consisting of many surface code patches in this way. So you cut your system into half and like fold it along the way, and fold it along the way, and fold it along the way. So this way you still have a quasi two-dimensional architecture so it's still not so difficult to build, and at the same time you can reduce the time cost all the way down to a constant. And another aspect about fault-tolerant quantum computation that is somewhat counterintuitive is that there is a little distinction between time and space. And there are many situations in which you can create a space over time, meaning that if you want to speed up your computation, you can maybe double the number of qubits and reduce the time cost by half. And this idea is particularly transparent in the case of photonic qubits, although I believe it's applicable in more general setups. So in photonic qubits, there is an option of storing some of your photons into some delay line, in which case delay line acts as a good quantum memory that stores your device, stores a quantum information. But the price that you have to pay is that the qubits, they have to travel along the delay line, so it adds a temporal cost. So overall, the name of the game is that the overall space-time volume of your computation remains as a constant, and you can tune the magnitude of the space or time depending on what you want to do. Obviously, you cannot reduce your space all the way down to single qubit. That would be ridiculous. So there's some minimum number of qubits that you need to absolutely have. But given that minimum, you can increase the size of your system if you want to reduce the computational time. So just to give you an example, if you use the naive version, RSGs, you can think of that as a version of number of physical qubits, because we need 24 million of them with a runtime of 1 day. But if you want to reduce the footprint of your device by, let's say, factor of 24, you can do that while increasing the runtime by a factor of 20. And there are these other scenarios which are kind of fun to think about. So the key takeaway is that, and one thing that before I forget, I should mention is that the point of this a constant time logical gates is that it reduces the overall space-time cost by reducing the temporal cost of the elementary gates from order D to order 1. And after that, you have these like various options to trade space and time given this reduced amount of volume. And especially in the regime in which we have like these large number of qubits where magic state distillation is relatively cheap, it looks like adding a bit of parallelization always helps us. So in that case, there's an interesting question of like, what is the best thing to do? Obviously, we don't want our device to be too large because that'll be more difficult to build. But if you want to make the device as compactly as possible, then this might incur some cost on the time that we can that we need to do useful computation. So I think looking a bit further term, I think there's a question about like how should we think about parallelization in fault-tolerant quantum algorithms. Yeah, so I think that's it. Thanks.
Great, thank you very much. Do we have any questions? If so, please raise your hand. Okay, so I actually have a question. So one trade-off that you're presenting here, right, is this like space-time trade-off where, well, you can basically do what you just said, right?
Mm-hmm.
But I was wondering, like the other, I think, obvious trade-off, maybe like harder to implement algorithmically, is I think the trade-off between the error rate of your device versus like how compact code you need. So like the higher the error rate, the kind of more like cycles you need to make it work. Mm-hmm. But I'm wondering what are some other trade-offs in this regime that people are thinking about? Maybe some that are not obvious to utilize today, but they might be in future if we like figure out how to get rid of some other roadblocks. Are there any other trade-offs like this that we could make use of someday? Or is this like space-time trade-off basically the most important one, and like probably there's nothing more to it?
I think space-time trade-off is probably the most obvious one. Mm-hmm. Other than that, I can only say things very speculatively. Mm-hmm. But I think so. Like if you do these logical error estimates for different gates, so at the high level you would expect them to be like very similar, but in practice they are actually different, and the error rate differs by like some certain like constant factors like 2 or 3. So actually, like depending on which operation you're gonna do, it might be advantageous to use one gate or over the other, because and that's the kind of study that hasn't been done very rigorously at this point.
I see. Makes sense. Any other questions? Okay, in this case, I wanted to thank you very much and close the official part of QRST. So